Hi, guys. How's everybody doing today?
Good, how are you?
I'm doing good, thank you. Oh, there we go. Just trying to get into the meeting here. So today we're going to finish up chapter 1.4. We started it Monday. We're going to finish it today. And then tomorrow, don't forget, we have a quiz on chapter 1.2, 1.3. Those homework assignments are due tomorrow at midnight. Okay, so keep that in mind for things coming down the pipeline. If you guys have questions on the homework problems, you can come to office hours tomorrow, or if we have time at the end of class today, we'll see. I can probably answer a question or two. Keep that in mind. And let's see how it's going. So we're gonna do, we'll finish 1.4 today. I'm looking at the calendar. We're gonna do 1.5 tomorrow, most of it, I believe we'll be able to do most of it tomorrow. And then on Wednesday, we'll finish up 1.5, answer questions on homework for 1.4, 1.5, things like that on Wednesday. Remember, next Monday, which is April 12th, we don't have class. There's no school, right? This is the day that the provost exchanged. We switched it with April 19th, right? Remember, 19th we normally have off, but they switched it so that we have off and we have to come to class on the 19th. But the 19th and the 21st, those will be our last 2 days of class, okay? So we'll have review basically for the final exam on the 15th, the 19th, and the 21st. Okay, so keep that in mind. If we have time, if you guys are interested, I can show you things from other parts of chapter 3 that we didn't cover. They won't be on the final exam, so I'll only do that like on our last day. So for example, if we don't have any questions. By the end of this week, probably on Friday, I'll start posting review materials for our final exam. I'm going to put them in the last week, our very last module, okay, which is where like I've got like the final exam, you know, information posted there on our very last module, okay. So I'll start putting review materials on that last module. I'll do that by the end of the week, okay. So keep that in mind. I think this week will be our last quiz, unless you guys want to have a quiz on Thursday the 15th. You guys can let me know if you want to have a quiz on the week of the 15th. I'm okay either way. It's up to you. The more quizzes you have, the more chance, the more things, you know, because I dropped the 2 lowest quiz grades, right? So then you have greater chance of bringing your quiz average up or down, I suppose, if you think about it that way. Anyway, so we started talking chapter 1.4 yesterday about how do we write out equations of the line, right? So we talked about, you know, we've always thought about when is our final? Yeah, so I don't actually check the final exam. I got burned really early on by checking the final early, and then the registrar switched it. So I don't check the registrar's date for the final until the last week of classes, because by then it's pretty stable. It's not going to change. So I actually don't know when our final is, and like I said, I'm not going to check it for like another week or so. If you guys check it in the registrar, it's probably stable. But like I said, I've gotten burned before, so now I don't check it until the end. So I can tell you in another week or so, but I'm not going to commit to anything right now about when our final is exactly. Okay, so lines. So we started talking about lines on Monday. We always think of straight lines as having the equation y equals mx plus b. I can rewrite this so that I have what they call an implicit equation for the line. A x minus x naught, b y minus y naught equals 0, where a and b are the components for the vector that's normal to the line, so it's perpendicular to our line, okay, where x naught and y naught are a particular point on that line, and x and y are generic. That's like our x and y from our mx plus b equation, okay. We can multiply these things out. Ax plus by plus c. C is just all the constant terms put together equals 0. That's our implicit equation. We call it implicit because the parameter t is implied. I can represent my line with a vector equation. Now my vector equation, I've got a point x naught, y naught, and my generic point x, y, and my v, my vector, is the vector that's actually, we call it parallel to the line. It's basically sitting on the line, and it could be any kind of scalar multiple of our line. Okay, t is the parameter. We plug in values of t in order to generate points on this line. Okay, so I can use this vector equation to break it down into component pieces, x and y, just my x components. This is called our parametric equation. And I can solve for t, set the t is equal, and I can get a symmetric equation. When we work in higher dimensions, which we're going to talk about today, higher dimensions than just the 2 dimensions that are listed here. When we work in higher dimensions, we must use the vector equation for our line, okay? Because we're using implicit and vector equations for things like planes and surfaces. Okay, so we're going to use our line vector equation. So we left off last time talking about example number 2, right? Which we were given, find an equation for the line in R2. So that tells us we're dealing with 2 dimensions, okay? Which is parallel to the vector 2, 3. That's like saying this vector is on our line, and it contains the point -1, 1. We're going to find and compare the vector symmetric and parametric equations. So I've got my vector equation. I solved for my components, my x and y, and I solved for t, and I set them equal to each other to get my symmetric equation. So the parametric equation, this is really good for testing. Excuse me. Where did that go there? So the parametric equation is good for testing intersections. We're going to see that in this chapter. We're going to talk about intersections of lines and lines, intersections of lines and planes, and then ultimately we'll get into planes and planes. I don't think we're going to talk about that today. So good for testing intersections, and it's also good for generating points on the line, right? So you can imagine I can choose a value for t. I can say, for example, like t equals 2, for example, and I'm going to generate my x equals -1 plus 2 times 2. 4 minus 1 is equal to 3. My y equals 1 plus 3 times 2. So 6 plus 1 is equal to 7. So a point on the line is 3, 7. Okay. Our symmetric equation, on the other hand, is good for checking whether or not a point is on the line, because I'm going to check to see if the equality is true or not, right? I'll plug it in. If the equality is true, equality is true, right? 3 equals 3, 0 equals 0, whatever, that means that the point is on the line. Otherwise, it's not. It's not on the line. So let's check. We're going to do 3, 7, right? So we'll check. We just generated 3, 7, so we know it is. But let's just go ahead and check it. So I'm going to plug in 3 for x. 3 plus 1 divided by 2 equals, and I'll put a question mark, 7 minus 1 divided by 3. So 3 plus 1 is 4 divided by 2 is 2. 7 minus 1 is 6 divided by 3 is equal to 2. Check. So 3, 7 is on the line. Let's, for example, I'll change it to be slightly, I don't know, so if I go something like let's check 5, 7 to see if it's on the line. So I'm going to go 5 plus 1 divided by 2, question mark, 7 minus 1 divided by 3. We kind of already have a feeling, right, how this is going to work. 5 plus 7 is 6, divided by 2 is 3. 7 minus 1 is 6, divided by 3 is equal to 2. So 3 is not equal to 2. So no, 5, 7 is not on the line. Right? Equality is not true. Equality is true. Okay. So there are different, benefits for each type of equation, but the parametric equation we're going to see today is really good for checking intersections. Does this line intersect another line? Does this line intersect a plane? We're going to all of that. Okay. So let's keep talking about our notes here. All right, so let's talk about planes. Planes Planes are a product of 3 dimensions, right? So in order to generate a plane, we're going to need 2 vectors and a point. Okay, I can, let's make sure that's in focus. Need 2 vectors and a point. Okay, so now let's draw this out. What does this look like? So I'm going to draw my plane here. Looks like a finite shape, but that's just because I'm not going to draw an infinite plane. But you can imagine, unless we've specified otherwise, our planes go infinite in all directions. So I've got my 2 vectors, v1 and v2. These 2 vectors, we're going to call them non-collinear. So non-collinear means that they're going to intersect somewhere, and they're both on the plane. Okay, and a point, we typically think of, I can write this as the point of intersection of these 2 vectors. Let's see, I'll write this as x naught, y naught, z naught. So this is our x naught, y naught, z naught. Everything has 3 dimensions to it, right? Because we're in 3 dimensions. And then our normal vector, oops, I'm going to cut off my z naught. I'm drawing my normal vector right here at this point of intersection, but it really doesn't matter because my normal vector, you know, it's going to be the same. I can even draw it facing down. These are all normal vectors, the same normal vector, right? It's all normal to this plane. Normal meaning it's at right angles too, okay? So I need this. My vectors, the vectors can be displacement vectors. Right, so we're going to see in later chapter sections, we're going to talk about, like, if I have 3 points on a plane, I can use that to generate 2 vectors, 2 displacement vectors, and choose one of those points as my origin point. And I'm going to use those 2 vectors to help me figure out what the normal vector is. Oh, excuse me, oops, this isn't working there. Okay, so now I can write out a vector equation for the plane. And this, I'm just going to give this to you. It's not often used, but I'm going to give it to you anyway, so you'll recognize it when you see it. We're more often going to use what we call an implicit equation for a plane, but I'll give you the vector equation. Similarly to our line equation, I've got x bar. I'm going to say x naught, so this is our point, x naught, y naught, z naught, plus t1, v1. This is our first parameter, t1, plus t2, v2. Okay, where v1 and v2 are our 2 vectors on the plane. I'm sorry, v1 and v2 are our 2 vectors on the plane. t1 and t2 are our 2 parameters that correspond to these 2 vectors. They could be equal to each other, they may not be, which is why they get assigned 2 different values. You could call them r and s or whatever variable you want, because this is a vector equation for a plane. So I need 2 vectors and a point. Like I said, it's not often used. More often, we use an implicit equation for a plane, and it's implicit because the parameters are implied. That's where the implicit comes from. So let me write it and I'll decode it. So I've got a, x minus x naught plus b, y minus y naught plus c, z minus z naught equals 0. Okay. Where, let's write a, b, c are the components for our normal vector. X naught, y naught, z naught are a specific point on the plane. We need a, remember we need we need 2 vectors and a point, or I can use a normal vector and a point. The normal vector can be derived from these 2 vectors. We're going to learn that in chapter 1.5. You don't know that yet. Okay, and now what I can do is I can multiply out, right? So let me just put a box around this. This is the one that we're going to use a lot. I can distribute my a, b, and c, and then combine all my like terms. So I'm going to get ax naught, plus by naught, cz naught equals 0. Then I'm going to group this, and I'm going to call this plus d, where my d is our constant term. So this was a minus axy by naught cz naught. And it's just, we just say plus d because really these x naught, y naught, z naught can be any number. So it may be positive or negative, it doesn't matter. But this is our implicit equation for our plane. We don't write implicit equations for our lines in 3 dimensions. Okay, so let's write our line in 3 dimensions. Okay, we must use the vector equation. Okay, because otherwise it's going to look like the plane equation. So we need to be able to use our vector equation. It's going to look the same for all intents and purposes, right? Where I still need a point and a vector on the line, right? But now I've got an X and I need to have a Y and I have a Z. Right, so this is my vector equation for my line in 3 dimensions. Okay. Okay. Let's take a look at our lecture examples for 1.4 again. Example 3 says, find an equation for there's a typo, find an equation for the plane, which contains the point. So let's start taking notes, x naught, y naught, z naught, and is normal to the vector. So this is our normal vector. This is our ABC. Remember, the components of our normal vector make up the coefficients for our x, y, and z. So let's write our implicit equation for our plane is going to be x minus x naught, b, y minus y naught, c, z minus z naught equals 0. Okay, so I'm just going to plug things in. So a, b, and c we have from here. X naught, y naught, z naught we have here. So 5, x minus 3 plus minus 3, y minus 1 plus 7, z minus a minus 2 equals 0. Now I can leave it like this. Technically speaking, this is totally correct. Sometimes we're asked to give it in like the completely multiplied out format. So let's go ahead and do that too. 5x minus 15 minus 3y, watch the negative, plus 3 plus 7z plus 14 equals 0. 5x minus 3y plus 7z. Let's combine our constant terms. Minus 15 plus 14 gives you minus 1. 3 minus 1 is equal to plus 2. So here is our equation for the plane. Now notice, coefficients for x, y, and z are the same components of my normal vector. It's how it's supposed to be, okay? If I have it in this form, you can see the point on the plane and the normal components. If I have it here, I'm going to have to, to generate the points on that plane, I'm going to probably figure out my intercept values. Yeah, so we're going to do that in example 4. So example 4 says, plane P is given by this equation here. Find a non-zero normal vector, so that's our n, to the plane and determine a point on the plane. They don't say anything about the points, so we're going to look at our intercepts. Those are always the easiest, right? If you got y equals mx plus b, set x equal to 0 and saw y equals b, that's a 0 comma b is a really good point on your line, right? So we're going to do the same thing for our intercepts for the plane. We're actually going to generate 3 points because we'll do the x-intercept, the y-intercept, and the z-intercept. So first, let's talk about our normal vector. Right, so this is just the coefficients of our x, y, and z. There, you're done, right? It's really nice and easy. You just extract out the coefficients for x, y, and z for your normal vector. So for our intercepts, they said to pick 1 point. We're going to give them 3 and they can pick which one they want. So let's do the x-intercept. And you should know how to do all 3 because in case it doesn't intersect the x-axis, you want to be able to find the y-intercept or the z-intercept. So x-intercept, I'm going to set y equal to 0, z equal to 0, and solve for x. So I'm going to go 6x minus 5 times 0 plus 3 times 0 equals, I'm going to add 7 to that side. So I'm going to get 6x equals 7 x equals 7, 6. So the point we're looking for is going to be 7, 6, 0, 0. Okay, that's your x-intercept. The y-intercept. Same process. We're going to set x equal to 0, z equal to 0, and solve for y. Okay, so I'm going to go 6 times 0 minus 5 times y plus 3 times 0 equals 7. That's going to give me minus 5y equals 7, y equals minus 7/5, which is going to give me the point 0 for x, minus 7/5 for y, 0 for z. Okay, my y-intercept. My z-intercept. Same thing. Set x equal to 0, y equal to 0. Solve for z. Okay, so 6 times 0 minus 5 times 0 plus 3z equals 7. 3z equals 7. Z equals 7/3, which is going to give us the point 0, 0, 7/3. So these are our intercepts, our x, our y, and our z intercept. Okay, we've found 3 points on the plane. They can choose whichever one they want. And don't forget, this we have the normal to the plane. Okay. All right. I'll let you guys finish writing that, and then I'll turn the page. So example 5. Okay, we've got this plane. It's the same plane equation we were dealing with before. Plane P. We want to find another plane equation for plane Q. Q has this point here, and Q is parallel to P. So I'm going to start taking notes. So Q is parallel to P. I'm going to draw that out. I like to picture it. Q is parallel to P. Okay, so I've got these infinite planes heading off like this. They're parallel to each other. So let's imagine P has a normal vector. Let's call this normal sub P. Q has a normal vector, normal sub Q. Okay, if P and Q are parallel to each other, then you can see the normal vectors are going to be parallel to each other. Okay. So that means, right, let's take a look. What is our NP? What's our normal to plane P, which is going to be 6 minus 5, 3. And our normal to plane Q, what do we have so far? I've got 3, B, and C. So I need to solve for B and C to find out what the normal is for plane Q. And once I've got the normal for plane Q and I've got the point that goes through, I'll be able to calculate what D is. Let's remember how we do 2 vectors that are parallel to each other. They must be scalar multiples each other. So let's set this up. So I'm going to say 6 equals R times 3. You could choose whatever variable you want. Minus 5 equals R times B. 3 equals R times C. It has to be the same R, but this one is going to help me figure out what that R is. So R is equal to 6 divided by 3, which is 2. Here, right, my B is going to be minus 5 divided by 2. My C is going to be 3 divided by 2, because I'm plugging in R equals 2, R equals 2. And then I solve for B and C. So now I have B and C, right? So my normal to my plane Q is 3 minus 5 halves. Oops, 3 halves. Okay, so now I can figure out the equation for plane Q. So I'm going to say 3x minus, let's do this, x naught, plus a minus 5 halves y minus y naught, plus 3 halves z minus z naught equals 0. And we're going to plug in 2, 1, 3 for the point x naught, y naught, z naught. So this is going to be 3x minus 2 plus minus 5 halves y minus 1 plus 3 halves z minus 3 equals 0. And then I'm going to distribute out my numbers because they want it in this form, not in this form. So I'm going to distribute out all my numbers. So I'm going to get 3x minus 6 minus 5 halves y plus plus 5 halves plus 3 halves z minus 9 halves equals 0. I'm going to group things. 3x minus 5 halves y plus 3 halves z. And now plus, I'm going to add up, right, my d is going to equal to minus 6 plus 5 halves minus 9 halves. You're going to find a common denominator, add all those up. You're going to find your d. I found my d was equal to minus 8. So plug it in, minus 8 equals 0. Okay, so there we go. We answered our question. But you had to recognize that if the two planes are parallel, then their normal vectors will be parallel. Okay. All right, write an equation for line L, which contains the point. Oh, so this is equation for a line. So this is our x naught, and is parallel to our vector. So this is really straightforward. Remember our vector equation, x naught plus t times v. What does this say? Of q by 2 to make the arithmetic easier, since scaling a normal doesn't change its direction and would describe the same plane. Yeah, yep, because you would get, well, I think you would want to, let me think. Yeah, you can do that. You can factor it out. You can multiply it by 2, it would just be a different scalar. Yeah, you can do that. Okay, so now, right, where was I? So I'm going to plug this in. So this is our vector equation for our line in R3, and we want it to contain this point here. So watch what I'm going to do. I'm just going to plug things in. Minus 2, 0, 3 plus t times 5, 7, 1. And then we're done. Right? Don't overthink it. You're just plugging in, right? You're coming up with the equation for your line in R3. The equation for the line in R3 must be a vector equation. They didn't ask us for it, but let's go ahead and do our parametrics just so we can see x equals minus 2 plus 5 times t, y equals 0 plus 7 times t, and z equals 3 plus 1 times t. There's our parametric. I'll do the symmetric. This was your answer here. I'm just giving you more information than we need, just so you can see how things can be broken apart. So my symmetric would be solving for t and setting them equal. So I'm going to go x plus 2 divided by 5 is equal to y minus 0 divided by 7, which is equal to z minus 3 divided by 1. And this is our symmetric equations. Okay, we weren't asked for these. I'm just giving it to you so you can see it. Okay. Let you guys finish writing that, and then we want to talk. Let's do a little bit of picture drawing and describing of stuff, but so we can start talking about intersections of things. Okay. All right. So let's think about intersections. Okay, so if I have a line and a line, let's talk, if we're in R2, my line and a line intersection is going to look like this. If they intersect, they will intersect in a point. If there's no intersection, then the lines are parallel. Okay. In R3, I can have intersecting in a point, parallel lines, which means they're scalar, their vectors are scalar multiples of each other. Or I can have what's called a skew line, which means, let me draw this out here. Let's imagine I'm going to draw my 3 dimensions like a cube here. Okay, so these are my 3 dimensions. You can imagine if I have a line here and this plane, and then I have a line here in the background on that plane. Okay, these 2 lines are not parallel and not intersecting. In 3 dimensions or higher than 2 dimensions, right? We can get this case where they're called skew lines. Okay, they're not parallel, they're not intersecting. And we're going to see what that looks like when we actually calculate our intersections of lines. We're going to do also planes too. If I have a line, so this is case 1, line, and let's say a plane, right? So I'm going to have, here's my plane. And then here's my line. They'll intersect in a point. Okay. If they don't intersect, we can have one of 2 cases. Here's my plane. Here's my line is on the plane, not intersecting. Line is on the plane. It's a form of being parallel, or I can have my plane and then my line is off the plane. Line is parallel to the plane. Right, remember this plane, I drew it finite, but it goes infinite out in all directions, right? So the line has to be parallel to it, right? There's no, you can't have like a skew line with the plane. It's going to be parallel to it. Even this plane here is parallel to this line, okay? So we've got a line and a plane. We are not covering in this class like lines and other types of surfaces, but you can imagine if I had a line in a circle or a line in a sphere, you know, depending on like the types of shapes that we're doing. The math still holds true for how we would calculate those intersections, but in this chapter only, we're just really talking about lines and planes. Okay, our next bit is a plane and a plane. These are the things that we're covering in this chapter. Other classes, we'll talk about intersections of other structures. So a plane and a plane, let me draw it out here. So if I have 2 planes that when they intersect, let's do this, it's gonna go like that. Oh, I'm not a very good artist here. Okay, and then we get this line of intersection. So here's plane 1. Here's plane 2. 2 planes intersect in a line. Okay, here's our line of intersection. So we're dropping down a degree, we're dropping down a dimension, right? So the planes are 3 dimensions, they intersect in a line. The lines are 2 dimensions that intersect in a point. You can kind of think about it in the back of your mind. If the 2 planes don't intersect each other, then they're parallel. Okay, which means that their normal vectors are parallel to each other. Okay, so parallel planes. Okay, so they intersect in a line or they're parallel. Okay, so these are the types of things that we're covering in this class. We're going to go into the cases on this, what this looks like, and then basically we're going to talk about not intersecting, what happens, and then we'll talk, I'll tell you a little bit of the detail, how you know which one you're dealing with, but for our class, we're only dealing with intersections or not intersections, and if it intersects, what's the point of intersection? Okay, what's the coordinate where they intersect? All right, okay. So let's talk about example 7. We've got this plane here and the line. Our line, we're just given 2 points for our line. So we've got a couple things we need to do. We want to determine whether the line is going to intersect the plane, and if it does, at what point. So the first thing that we need is we need an equation for our line. So I'm going to use obviously a vector equation. Okay, so I need V. V is going to be my displacement vector between the 2 points. Remember, displacement vector is terminal point minus my initial point. Now, I didn't tell you it starts here and it ends there. If you're not told, it's up to you to choose what's your initial and what's your terminal, okay? It doesn't matter. What's going to happen is if you choose this as your initial and this is your terminal, your vector goes from here to here. If you choose this as your initial and that's your terminal, you get the same vector but opposite direction, okay? So it doesn't matter, but what does matter is identifying which one you want to choose as your initial point, because this x naught is your initial point. So make sure, I usually make a note of it, like which one did I choose as my initial point, because that's the one I'm going to put into my equation. Okay, so like I said, I sort of randomly chose this one. So I said 5, I'm sorry, whoops, that's my initial point. So I'm going to go terminal 6, 2, 2 minus my initial 5, 3, 0. So I'm going to get 6 minus 5, 2 minus 3, and then 2 minus 0. So this is my V, my vector on the line. My initial point is going to be 5, 3, 0. So my equation for the line, x bar equals 5, 3, 0 plus t times 1 minus 1, 2. So that's an equation for the line. I need that to figure out if the line's going to intersect the plane. Do they intersect? So what I need to do is I need to take my line and I'm going to break it down into parametric form. So I'm going to break it into components. So x equals all of my x components, 5 plus 1 times t. Y equals 3 minus t. And z equals 0 plus 2 times t. I'm going to take this and I'm going to plug it into my plane equation. Right, my plane equation, which we gave as 3x plus 2y minus z plus 6 equals 0. So wherever I see an x, I plug in 5 plus t. So I'm going to go 3 times 5 plus t plus 2 times 3 minus t minus z, which is 2 times t plus 6 equals 0. Okay, so now my goal is to solve for t. Okay, so let's distribute this out. So I'm going to get 3 times 5, 15 plus 3t plus 6. Now watch out for the negative, minus 2t minus 2t plus 6 equals 0. So let's combine things. So that's minus 4t plus 3t gives me minus 1t, so minus t. This is 15 plus 6, that's 21, plus 6 is 27. So I'm going to get t equals 27. I'm going to subtract the 27, divide by minus 1. So I get t equals 27. So here's a little clue. Now, the t's did not cancel out. T's did not cancel out. Therefore, line and plane intersect. Okay. If the t's cancel out, the line and the plane don't intersect each other. We're going to talk about what that looks like in a minute. Okay. But if they do not cancel out, I have a t. That means that they intersect each other. Now I can look for our point of intersection. So I can use my parametric equation and plug in the t. So x equals 5 plus t. 5 plus 27, which is 32. Y equals 3 minus t. 3 minus 27. So 3 minus 27 minus 24. Z equals 2 times t, which is equal to 2 times 27, 54. So our point of intersection, our coordinate for intersection is 32, minus 24, 54. Okay. You guys finish writing that, and then we'll summarize this. What do I mean by the t's do not cancel out? And if they do cancel out, what does that mean? Okay. All right, so we were talking about this right here. We have a line and a plane. So if they intersect in a point, let's write this down. I'll write it in purple. It's a little darker. So when I'm solving, we go through the same process that we just did, right? Where we have the vector equation for a line. I break it down into the parametric equation, take my x, y, and z, plug it into my plane. And then if they intersect, the t's do not cancel. You can solve for t, and then t equals some number. You can use that number to plug it in and find the coordinate. If they don't intersect, the t's cancel out. Okay. Now, if the line is on the plane, so let's do this. Let me write it down like that. I'll write it down separately. I think it's a little too busy here. So it's on intersection. Okay, so 1, if t does not cancel out, then yes, intersect. Use t to find point of intersection. Okay, we just said that. If t does cancel, then there are two things, and that means that no intersection. Okay, but there's differences. If the equality is true, so say I get 3 equals 3 or 0 equals 0, that means that the line is on the plane. If the equality is false, so it'll look like 3 equals 0 or something. If the equality is false, 3 equals 0, then the line is above the plane. Both cases, this is a case where they're parallel. Line is parallel to the plane, okay? But it's either on the plane or it's above the plane, okay? But in essence, you just have one of two cases. If the t does not cancel out, they intersect. If it does cancel out, there's no intersection, no point of intersection, okay? Let's run through some examples. First, we're going to do two lines intersecting each other, and then it looks like, yeah, it looks like we're just doing two lines intersecting each other. And then we're going to get into, in chapter 1.5, we're going to talk about lines and planes intersecting each other, okay? So in more detail. And then planes intersecting planes. Okay, so let's do this. Two lines intersect each other so that you can see. So I've got a vector equation for line 1 and a vector equation for line 2. So this is good. We're going to get a chance to see what it looks like. So what I want to do is I'm just going to check to see these two here. Are they scalar multiples of each other? So my two vectors are v1 parallel to v2, right? So I'm looking at -1 to 0, 0 to 3, and 1 to 1. So no, I'm going to go with no, they're not parallel to each other. I can't find the component that's going to make it work. The r is not the same. Okay, so no, they're not parallel to each other. So now I can say I'm going to go L1 and parametric form. So I'm going to go x equals 0 plus a -1 times r. Y equals 3 plus 0 r times r. Z equals 1 plus 1 times r. Okay, and then my line 2, x equals 0 plus t times 0. Y equals 0 plus 3 times t. z equals 2 plus t times 1. Now, if they intersect, then x equals x, y equals y, and z equals z. We have to solve for parameters for r and t, and then we have to check if valid. Okay, so let's set them equal to. So I'm going to go minus r equals 0. This is our x. Then my y's, this is our x. My y's, 3 equals 3 times t, which means t, r equals 0, and t equals 1. And now z, I'm going to go 1 plus r equals 2 plus t. So this is our check. So I'm going to go 1 plus 0. Oops, sorry, that's a 1. 1 plus 0 equals 2 plus 1. 1 does not equal to 3. Okay, so this is not true. So the lines don't intersect. Well, lines that in 3 dimensions that don't intersect each other and they're not parallel, not intersecting, are skew lines. Right, remember our skew lines. Right, I've got a line here. I can say L1, and I have a line here. That's L2. Okay, they're in different planes essentially. Okay. Skew lines look like that. Okay, so let's do this one. Oh, look, we have a vector equation and an implicit equation. These are in R2. So this is R2, that one was R3. So this, let's just check the vectors. So this is V, and then I'm going to get the normal vector here. So my V is equal to 2 minus 1. This normal vector is 1 comma 2. Oh, I know a trick. So what happens is to get the vector, we're looking like this. Here's our vector. So to get the vector that's normal to this line, right, what I need to do is I have to switch the x and the y and negate the y. So to get the normal, in 2 dimensions, in 3 it's more complex, but in 2 dimensions I can switch them, right? I can go minus 1, and I'm going to negate that one. But this is, they're the same vector, but just pointing in the opposite direction, right? That's equal to that vector. So this is actually the same line. Okay, so this, we just did a quick check on the vectors, and we can see that they're the same line. But let's go through and we'll do the intersection so you can see how it's not going to work. So we'll try the intersection so that you can see how the process won't hold. So I'm going to take L1 and I'm going to break it into components. X is equal to 3 plus 2 times t. Y is equal to minus 2 minus 1 times t. And I'm going to plug that into L2. So x plus 2y equals minus 1. So I'm going to go 3 plus 2t plus 2 times minus 2 minus t equals minus 1. So this becomes 3 plus 2t plus minus 4 minus 2t equals minus 1. Look, the t's cancel, and I'm left with minus 1 equals minus 1. So t's cancel, so no intersection, which means these lines are parallel, right? Actually, they're equal to each other because the equality is true. So it's the same line. Okay, we figured that out up here with our trick of figuring out the vector that's perpendicular to this one was the same vector, right? So we're looking at we've got the same line. So it's just a different way of writing the same line, but we did the intersection to prove it to ourselves. Okay. I'll give you a hint on this one. They actually intersect each other, but let's go ahead and do the same thing. So we're going to do, so this one has a vector v, which is 2 minus 1. This one's normal vector is 1, 3. So they're not going to be equal to each other. But let's go ahead and check. We're going to do the intersection. So L1, I'm going to break into component pieces. X equals 3 plus 2 times t. y equals -2 minus 1 times t. And that's going to go into L2. So x plus 3y, 3 plus 2t, plus 3 times -2 minus t equals -1. 3 plus 2t minus 6 minus 3t equals -1. So let's combine. So I'm going to get 2t minus 3t, so it's minus t. 3 minus 6 is -3. Add 3, add 3. So minus t, so t equals -2 in the end. I can use this, so there is a point of intersection. Okay, I can use my t to figure out the point of intersection. X equals 3 plus 2 times a -2. -4 plus 3 is -1. Y equals -2 minus a -2. -2 plus 2 is equal to 0. So we're looking at -1 comma 0 is our point of intersection of L1 and L2. Okay. And that's basically it for chapter 1.4. We're going to cover 1.5. We'll start that tomorrow, and then we'll wrap it up next week. Okay, and we'll go over homework for 1.5 and 1.4. Okay. Phew, a lot of stuff, right? But tomorrow, 1.5 is really interesting too. Right.
I'm sorry, could you go back to example A for a second?
Which part, A, B, or C?
A.
A, okay, yep.
Great, thank you.
So we have a few minutes. Does anybody have any questions on the homework for 1.2 and 1.3? There's something I wanted to mention on, I think it's 1.3, that the work, that if we're dealing with work, this is really ridiculously easy, but work is the force dot the displacement. If they're two vectors, this is force and displacement, right? It's really straightforward. So you're just doing the dot product to calculate your work. All right, what is that? 1.3, number 22, sure thing. Yeah, 22 and 23 are like logic puzzles. So let's, so this is 1.3, question 22. So we were given a bunch of stuff, like the magnitude of A was 2, magnitude of C is equal to 5. And so what I can do is, and then we were told even A dot C is equal to, what did we say, 3. So we're given this one as A over magnitude of A dot C over magnitude of C. Okay, so now I'm just going to do this. I'm going to say A dot C all over the magnitude of A times the magnitude of C. So A dot C, they gave me as 3. Magnitude of A is 2. Magnitude of C is 5. It's just 3/10. It's the same thing as, it's a logic puzzle for 23 as well. 1.2, number 45, sure. Okay. So 1.2, question 45. So this one, we're told we have a mass, which is 3 kilograms, and it's on the ground, right? And then there's, we've got gravity. We've got the force due to gravity, right? So gravity is minus 9.8 meters per second squared, right? Or it's really 9.8 meters per second squared, but because it's pulling down, it's negative force. And then we're told that there's an upward force of 30 newtons. And so they wanted to know, is it accelerating upward or downward, or is it impossible to tell? So let's first figure out the force due to gravity. And that's going to be our mass times acceleration. 3 times minus 9.81, which I got 29.43, and it's negative. And this is in newtons. It's kilogram meters per second squared, so that's newtons. So I'm going to figure out my net force. So I'm going to go 30 plus a minus 29.43. I get, what I get minus, I'm sorry, plus 0.57. It's positive, so it's going up, right? Because it's positive. So now if I want to figure out the force equals mass times acceleration, so this is going to be my net force. So I'm going to say 0.57 equals 3 times the acceleration. My acceleration is, this was what I get, 0.19. It's positive, so it's accelerating up. Really, really, it's a really small number, but it's going up. 1.3, 23, USD 23. Okay, we'll do 23 also. All right. So, yeah, 1.3, question 23. Okay, so this is the same one. So we're told, what's the magnitude of a plus 5 times b? And they gave us the hint. They said the magnitude squared equals v dot b. So we're going to exploit that. So a magnitude is, remember, we're going to go a plus 5b squared square rooted. It seems like, oh, I should just take it. It's just a plus 5b. Well, I'm going to actually, I want to square this out because that's going to help me given all of the givens that they gave me. Does that make sense? So I'm going to go a plus 5b, a plus 5b, and I'm going to FOIL it out, right? So if I FOIL it out, what am I going to get? I'm going to get a times a, which is a dot a, plus 5ab plus 5ab plus 5 squared, 5 times 5, b dot b. Now, they gave me, there were some givens. So the givens that they gave me was a dot a. They said that was the magnitude squared. So the magnitude of a, right? So the magnitude of a squared, that's just going to be, they gave me the magnitude of a was equal to 2. And that's going to be the same thing for b squared. So then they also gave me a times b, a dot b was equal to 0. So a dot b is equal to 0, a dot b is equal to 0. A dot a is the magnitude of a squared. So this is 2 squared. This is 25 b dot b. So then we're told the magnitude of b is equal to, let me get this right, is equal to 1. So this is 1 squared. So I'm left with 4 from 2 squared plus 25 times 1 squared, which is just that. It's like, it's a logic puzzle more than anything. Does that make sense? You're kind of working it through, but this is the hard part that, you know, right? The magnitude means, right? I'm going to take these components and I'm going to square it. You're squaring it as a block. Think about it like this, which means I have to FOIL it out. Can we use the dot product to see if things are parallel? No, use the dot product to see if things are perpendicular, because the dot product will be 0 if they're perpendicular. To check to see if things are parallel, you have to check, you're talking about the vectors. I think this was one of the questions on here. I think that was a whole set of questions. There was a whole page. It was like 27 through 30. You use the dot product to see if they're perpendicular, right? So if the dot product is 0, then they're at right angles to each other. If the two vectors are scalar multiples of each other, then they're parallel. Any other questions on the homework, you guys? 1.2, 1.3? If you guys don't have, oh, 1.2, number 46, sure. Okay. Give me a sec to find it. 46, yeah. So this one, you have to use the gravitational constant in the equation that we did in chapter 3, I think, when we talked about work. So, so this is 1.2, question 46. So we're given a point mass A is equal to 3 kilograms, and we're given a point mass B is equal to 5 kilograms. And then we're told that this is at displacement. It's at position 1, 2, 3, and then this is at position B 1. Oops, sorry, this is 257. 5, 7. Yeah, what's the gravitational force vector does A exert on B? So we're looking at A onto B. And so the force of A onto B is going to look like the equation that we talked about in chapter 3 was going to go G, or gravitational constant, mass A, mass B, and then the square over the square of the distance between them. So let's see, I'll write this as d squared. And then what we want, because this is a force is a vector, we want to multiply this by d all over the magnitude of d. This is to make it a vector. So now d is equal to, this is a d. D is the displacement vector between MA and MB. So now what we're going to do is we're going to say it's going to be, we're going from A to B. So I'm going to go this minus this, right? So I'm going to get 257 minus 1, 2, 3. It doesn't matter if you go either way because we're going to, it's just whether it's exerting this way or exerting that way. So I'm going to go 2 minus 1, 5 minus 2, 7 minus 3, right? And then the magnitude, let's do the magnitude of d while we're here. So this is 1 squared, 3 squared, 4 squared, 1 plus 9 plus 16, radical 26. So we figured out the magnitude. So now what's going to happen is our gravitational constant we were given in chapter 3, which is 6.67384 times 10 to the minus 11. I forget the units for that. So now our force, I'm going to plug things into here. So now our force is 6.67384, 10 to the minus 11 times 3 times 5 divided by, right, this squared. So this is like radical 26 squared times 1, 3, 4 divided by radical 26, right? Because we want the unit vector. So now this is going to be really small. Look at that there. So this is going to be, I'm just going to leave it 3.85 times 10 to the minus 11. And I'm going to distribute this. So 1 radical 26, 3, 4. Okay. Okay, guys. All right, 1.2, 1.3 due tomorrow at midnight. Those are the basis for our quiz questions. Tomorrow. Carrie asked really quickly. We'll do 43 really quickly. So 1.2 question 43. So we're given the magnitude of V equals 3, and it's going to have the same direction as 1, 1. So I have to figure out what the direction is of 1, 1. So it's going to be 1, 1 divided by its magnitude, which is 1, 1 divided by 1 squared plus 1 squared square rooted radical 2. So this is 1 over radical 2, 1 over radical 2. So that's the direction of this here. So we want this to have that direction, but we want it to have the magnitude of 3. This is a unit vector, which has magnitude equal to 1. So I'm just going to multiply to get magnitude equal to 3. So this is equal to 3 over radical 2, 3 over radical 2. So this has magnitude equal to 3, and then direction equal to 1. You'll see that if you take out the, if you do the direction on that there. Okay. Okay, guys. Have a great day. I'll see you guys all tomorrow. Bye.
Thank you.
Take care.